Okay, so continuing with our effort in chemical kinetics, we have to date looked at some of the introductory concepts. On the first day we talked about describing rates of reaction. What are they? How we describe and study reactions and changing concentration over changing time in the kinetic world. And then went on through, and so we've talked about rate as a function of concentration. We haven't really emphasized rate in nature yet. You'll see more of that developed in the laboratory, in which we'll use, and I'll show you a demo on it in just a few minutes. So we want to finish the idea of concentration right now, which is the decay process. So we had three problems types for rate and concentration. Just to, you have one which is rate averaging, and then a second type of problem. Please mark these down if you don't know, because this is how I build an exam. Okay, so please make note. Rate averaging, and then rates proportional to equation, balanced equation, coefficients, and then empirical rate laws, and those are 3 of 4. In which, in the last case, this empirical rate law, we use a little table and experimental, come up with the material we have on the board. If that's not familiar, please jot it down and learn it. Okay. The fourth area in this collection is the decay process. Okay, of a reaction. So we begin and go through how to deal with that. When we started the work on kinetics, or the study of reactions in general, I drew a graph for you. Looks something like this. As a function of time, and you're changing concentration at time equal 0 seconds, hours, years, whatever, still 0. Typically time is in seconds to some future point. We have a 100% concentration of our reactants. The concentration of product equals 0% at t equal 0 seconds, if you will. We can put it in like that if you like. Think of this as putting the reaction in a starting gate. You have not allowed A and B, or whatever the components are, to react. Then mentally you open the gate and let the reactions run like horses coming out of a starting gate at a horse race. Logically, for a reaction going to products, reactants going to products, sorry, you will observe a trend like such, and where the reactant concentration decreases as a function of time. Of course, you would also see the product concentration increase as a function of time also. Now, in chemical kinetics, our primary focus is on the reactant side. So when we talk generally about the behavior of a reaction, we define its reactive behavior or rate behavior in terms of the reactant. So simply in terms of reactants, and I'll try to be neat. What we see is a trend that does this. And in an ideal world, it would eventually go to zero, but it levels out and gets real close to the axis. So this is the decay of reactant concentration as a function of time. Well, this is what we call a classic decay curve. Put that. And the evaluation of this curve is derived from a change in the concentration. Okay, where's the concentration at some point in time as a function of time? Okay, so we come up with an equation. I'm not going to derive this. It's pointless. I'm not going to ask you to derive it on test day. But the classic decay curve is described by what we call C equals C sub O base to the natural log e to the minus kt. And I'll put C sub f right there. Cf is the final concentration, or concentration at time t. Okay. C0 is the initial concentration. K is the reaction rate constant. And T is the time you were interested in, how long the reaction is being considered. We're going to learn how to predict, given the variables on the right of the equal sign over here, what the final concentration is. We're also going to learn from this equation. Well, let me get problem types. How about that? One of them is predict CF at time t given K. All right. This is a first order. I forgot to mention that. This is a first order decay equation. And there is also a second order decay equation, but we're not going to work with that. Okay. Radioactive decay is also first order. We'll get to that in time. So that's one type of problem. A second type of problem is how long, time-wise, to obtain given C final, like that. Now there is a second type of equation that comes out of this equation, which would represent the third and really the fourth type of problems. We call it half-life. The half-life equation will allow you to actually calculate a time for C sub O over 2, where you will divide the original given concentration in half. How long does it take for the original concentration to go to 1/2 its original concentration? That's called half-life. And if given the half-life, however, you can calculate, CA meaning calculate the rate constant. So you really have two problems out of the half-life equation. Okay, and the half-life equation is KT equals 0.693, and T has a subscript of 1/2, like that. So you have two equations to use here, and this one right here to work about 4 types of problems. Now, data may be given in half-life. Let's say you're given a half-life, but asked to calculate something for this equation up here. Calculate a concentration after a period of time. Well, you'll need the K value. So what you will use is this equation first to calculate K, and then apply it up here. We'll see that in just a minute. Okay. I need to pause until I can. Okay, if you would look with me, and we're going to look at some problem types here real quickly and see this one that starts with sulfuryl chloride. Right here is a half-life decay type problem, the decay equation type problem, where you start with sulfuryl chloride and decomposes when heated according to that. In an experiment, the initial concentration was this. If the rate constant is that, what's the concentration after 2 hours? So you see, one of the problems is what is your C final after 2 hours? And we're going to work through that kind. And a second type of problem, ethyl chloride, given here, used to produce tetraethyl lead gasoline additives, decomposes when heated according to that equation. The reaction is first ordered, which tells you use the first order decay. You'll use that equation, the one we showed you. In an experiment, the initial concentration was this. After heating for 155 seconds, see, they give you a time. This was reduced to this. What was the concentration of ethyl lead after 256 seconds? Okay, notice in here what they don't give you. Okay, they don't give you the K value, do they? Let's see. The reaction's first order. The initial concentration was this. After heating for 155 seconds, this was reduced to this. What was the ethyl lead after 256 seconds? So I'll show you how to deal with that. You've got the initial, you've got the final, you've got so many seconds, okay, so forth, and you solve for the unknown. Okay, let me show you the other kind. Okay, in the next page, In the presence of an excess thiocyanate ion, the following reactions first order in chrome, the rate constant is given here. What's the half-life? So you'll have to use the half-life equation here. How many hours does it take to go from, say, an initial concentration of 100% to 25%? Well, 50% is one half-life. So you calculate the half-life, and that's how long half-life. I need to emphasize this. I didn't do this earlier on half-life. Okay, let's take our graph. Concentration, and let's generate a first order decay trend like this, and this is 0. Okay, this is what we call C initial concentration, whatever the problem gives you. 100%, usually it's a number, but sometimes it's just percentage, and then you assume 100%. Well, when does it go to half? Well, here's 100%, that's 0% right there. Why don't we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why don't I bring it down 1 and kind of there, get rid of that one. So we can be at least reasonably accurate. 1, 2, 3, 4. Right here, that's C sub O over 2 right there. So what you do is you come across, hit the graph, and come straight down, and that's T to 1/2. That's your half-life. That's the time it takes to go to 1/2 of the original concentration. It's also called first half-life. Now, from C sub O to, from that point to half of what's left, 1, 2, 3, 4, 5, 1, 2.5, right there, that's 1/2 of C sub O over 2, or 25%, 1/4. See the 25% in there now? Check mark that if you don't, study it. So this is the second half-life. Or 2 half-lives. And if we went down and split it again, we would have a third half-life. Go way on out here. Okay. Issue number 1. Listen to this very carefully. If you're not listening, hadn't listened yet, listen to this. Doesn't matter which of those half-lives you're considering. All half-lives are the same amount of time. What I mean is the time it takes to go from C0 to Z half-life may be 30 seconds. Going from CO over 2 will also be 30 seconds. Going from to the third half-life will also be 30 seconds. And splitting that in half will also be 30 seconds. So a given half-life, regardless, is a start to finish time all the same. Now, that's one issue. A given half-life is always the same. Now, the problem is how they word the problem. How long does it take to get to the third half-life? You see what I'm saying? So it's asking you, how long does it take to get to the 1/4 point here? And half-life, and then the decay equation deals, listen, with what's left. Not what you start with or how much is used up. I see you glaring. The half-life and the equation, decay equation, deal with what's left, not what's used. Please check that. What's left, not what is used. So when that C final is what's left.
What do you mean by what's left? Like, say for 25, would you do the 75? Is that my answer?
Well, in my example, it would be to the time it would take to get to the 20, where 25% remains, is 2 half-lives, 60 seconds. How long does it take to get to that point? That's the way a question might be worded. Another question may say, what is the half-life? And they'll give you the K value. It doesn't matter. Half-life is, you are assuming a point to a point. Half-life's the same. The half-life equation itself is this, just for the half-life. It doesn't have any concentration terms in it. So it's independent of the concentration. So all half-lives are the same. The difference is, we say first half-life, it goes to half, 50% remaining. Second half-life, 25% remaining. Third half-life, 12.5% remaining. Listening? You listening, or you going to sleep on me, huh? You reckon you're listening to me? Okay. So if it's, the problem asks you, how long does it take to get to where 12.5% remain? That's 3 half-lives. 3, 6, 90 seconds in my example. Okay? So there's a double-edged sword here you want to be careful with. One is all t to the 1/2 values are equal. Okay? But the second one is how long to change concentration from C1 to C final, CO to C final. This problem is the sum of your individual half-lives. You calculate each one, add them all up. So you get a double-edged sword there you want to be careful with. Yes? Nod for me. It makes sense to you?
Sorry, what?
Huh? A half-life, notice, in itself is all the same. I don't, did I make a mistake?
Sorry, I missed the last thing you said.
Huh?
About the sword. Sorry.
Okay. Is everybody on the same page with me now?
I think an example would kind of help things.
I just gave you one.
Well,
a reaction.
Well, like
given a half-life. You calculate it, you'll come up with a number.
Wrong.
I will. I got one here. I got one here. Say the problem gives you, you calculate a half-life 30 seconds. What does that mean? It's the time it takes to go from 100% to half.
Right.
Okay? Now, that second concentration, even though it's half of what you started with, is a starting point again. A new starting point. So from that new starting point, how long does it take to cut that one in half? 30 seconds. The same half. Think about it. They're all the same. But if I ask, how long did it take to go from C0 to 25% remaining? 60 seconds. You had 2 half-lives involved. Study that. I can sit here all day long and say that. And if it's not registering, you need to go by yourself and quietly meditate on the issue It'll come to you. Half-life is a constant, but the time to a given concentration is multiple half-lives. Multiple half-lives.
Can you give us a problem to work
Yeah,
with?
let's see.
I will work some problems at appropriate times. I'm presenting a theory right now. I've given you enough that you need right now. Okay. Continue with this. We'll work some of the problems on the kinetics decay. Let's start with the sulfuryl chloride problem. Right here, sulfuryl chloride decomposes when heated according to the following process. In an experiment, the initial concentration of sulfuryl chloride was given to be 0.0248 mole per liter. If the rate constant is 2.2 times 10 to the minus 5, what's the concentration of sulfuryl chloride after 2 hours? Now, one of the things you have to take into account here is the units of the rate constant versus the units of the time factor. One's in hours and one's in seconds. You have to convert seconds to hours or hours to seconds. It's much easier, in my opinion, to convert the hours to seconds. So, for this problem, we're given SO2Cl2 as a gas goes to SO2 as a gas plus Cl2 as a gas, and we're given the initial concentration C sub O of SO2Cl2 at T equal 0 seconds is equal to 0.0248 mole per liter, and they give us the rate constant K 2.2 times 10 to the minus 5 per second, which can be written as the same as 2.2 times 10 to the minus 5 seconds to the minus 1, if you wish. What's the concentration? Calculate molar concentration at 2 hours. Now I'm going to convert that to seconds. 2 hours times 3,600 seconds per hour gives 7,200 seconds. So we are in the same units in the problem. So what is the final concentration at 2 hours, which is final concentration at 7,200 seconds, and that's C sub O E to the minus K T. So I'm going to come back down here to equal C sub O was given to be 0.0248 mole per liter right there. Then we'll go E to the minus K value. Here's the K. E to the minus, now I like to bracket this, 2.2 times 10 to the minus 5 seconds to the minus 1 times 7,200 seconds, and close the brackets right there. Now that is reciprocal to that, so that will cancel out. The only units remaining will be moles per liter. So by solving this expression first, we wind up with 0.0248 mole per liter, and this e to the minus 2.2 10 to the minus 5 times 7,200 is 0.854 for that term right there. And then when we multiply these two together, we get the final concentration at 0.0212 mole per liter. Okay, so that's the first decay problem we wanted to look at. The next decay problem is the ethyl chloride problem. Ethyl chloride is used to produce tetraethyl lead gasoline additive and decomposes when heated to give this equation right here. The reaction is first order, therefore we'll use this first order decay equation. In an experiment, the initial concentration of ethyl chloride was 0.001 molar. After heating at 500 degrees for 555 seconds, this was reduced to 0.00067 molar. What is the concentration after 256 seconds? Well, this problem works in two parts. One, to calculate the K value based on the concentrations given at 155 seconds, and initially, and of course 155 seconds, you calculate the K value. And once you get the K value, then you can calculate the concentration after 256 seconds. So in this problem, we're given ethyl chloride heated at 500 degrees goes to C2H4, looks like ethylene, plus HCl, also a gas. Of course, the reaction is first order. Therefore, use C equals C sub O e to the minus KT equation. Okay. Now, in the experiment, the concentration of ethyl chloride was given to, so C sub O at TO is equal to 0.00100 molar, and C2, if you would, at T equal 155 seconds is equal to 0.00067 molar. So from this we can calculate the K value in the following way. So C equal C sub O e to the minus KT. Now, solving this expression for either K or T, typically if you're solving for K, you'll find out that K is equal to ln of C over C sub O over minus T, or if you're solving for the time factor, then this would be ln of C over C sub O over minus K. So, of course, we're using the ratio of concentrations and the time factor. 155 is what's given. These two And so we get the K value, and the K value, then we'll turn around and calculate the concentration at 256 seconds, which is the outcome of the problem. So using K equal ln of C or C sub O over minus T, we have ln of C, which is 0.00067 molar over 0.00100 molar, molars drop out, divided by a time factor of 155 seconds. We obtain a K value of 0.0025 seconds to the minus 1. Now that's part A. And now to finish the problem, say part B, we'll use this K value in calculating the concentration of 256 at 256 seconds. We want to find out what C equals C sub O e to the minus KT, and so we want to put that in, but now we have a K value which we can put into the equation right here, and then the initial concentration from up here, we can solve a problem that's being asked. So we have 0.00100 molar right there, E to the minus K, which is 0.0025 seconds to minus 1, times 256 seconds, which is the ultimate question, like that, and we get 0.00100 molar times, now that E to the minus product of this issue of KT here is 0.5272. So about half, this is cutting about half, is what this is a concentration reduction factor, some people call it. And so this will ultimately come out to be 0.000527 molar at 256 seconds right there, which, if need to, times 10 to the minus 4 molar at 256 seconds. So that's the second problem in our set. Now the last problem in this set, it deals with half-life and the interpretation of half-life. Now what I'm going to do is illustrate this one. It says, in the presence of excess thiocyanate ion, the following reaction is first order in the chrome 3. The rate constant is 2 times 10 to the minus 6 per second. Here's the equation. What's the half-life in hours? How many hours would it be required for the initial concentration of chrome to decrease to what's 25% remaining, 12.5% remaining, 6.25% remaining, and 3.125 remaining? So we calculate the half-life. Now the half-life would be, of course, the time it takes to reduce the concentration to 50%. So that's what it's called the first half-life of the reaction. So in this problem, we're given chrome 3 plus aqueous plus the thiocyanate SCN minus aqueous combines to chrome thiocyanate 2 plus aqueous ion right there, and you're given the rate constant K, 2.0 times 10 to the minus 6 seconds to the minus 1 reciprocal seconds. Now the half-life equation is kt to the 1/2 equals 0.693. It's derived from the first order decay equation. Okay, so to get the first half-life, that would be t to the 1/2 is equal to 0.693 over k, which is 0.693 divided by 2.0 times 10 to the minus 6 seconds to the minus 1. So that is reciprocal, will come out, the entire term will come out in seconds. So the first half-life comes out to be 3.47 times 10 to the 5th seconds. Now, in order to understand how the problem, to answer the problem for 25% left, 12.25% left, 6.25 and 3.15 left, we have to consider adding half-lives. The first half-life is the value we just calculated right here, 3.47 10 to the 5th seconds. To get to a quarter remaining, that's a second half-life. Well, all half-life periods are the same. So if the first half-life is 3.47 times 10 to the 5th, to get to half, it'll be another 3.47 times 10 to the 5th seconds to get to the second half-life, or 25% remaining. It'll be 3 half-lives to get to 12.5, 4 half-lives to get to 6.25, and 3.125% to get to, that'll be 2, 3, 4, 5 half-lives. Okay? Now, I've drawn the standard first order decay. If we assume this is first order decay, second order decay would just drop down faster, and third order drop down even faster. But let's say this is our first order decay equation. Now, this point right here is the halfway point on the concentration axis. That is C sub O over 2. And if we come over to the graph right there and then straight down to this axis, this will be the first half-life right there. So the time that it would take to get from here to down to here is referred to as the first half-life. We'll make us a little graphic line here to illustrate this. Bring this into focus. Go ahead and just across here like that. So the time it takes to get to here, from here to here, this is the first half-life and is equal to this 3.47 times 10 to the 5th seconds. Now when we talk about the second half-life, it'll still be 3.47 times 10 to the 5th seconds, but we're going to half of this. So second half-life would go 1, 2, 3, 1, 2, 3, 4. I think that's, set that back up right there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 1, 2, 3, 4, 5. So this point right here would be your point for your second half-life. So we'll draw a line straight across to the graph, mark that point, and then come straight down to the horizontal axis, the time axis. And there is the point where is the second t to the 1/2. Now, one of the things you need to understand is the time to get from the c sub o over 2 down to the second half-life, which would be c sub o over half of this c sub o over 2, 1/2 of that, which turns out to be 1 or 1/4 of c sub o, or 25% remaining at that particular point. Okay, now this time bracket is 3.47 times 10 to the 5th seconds. Now, to the second half-life bracket is also 3.47 times 10 to the 5th seconds. But the time it takes to get to the second half-life is the sum of these two values, which is 2 times 3.47 times 10 to the 5th seconds. And that, of course, 6.93 times 10 to the 5th seconds. So it takes 6.93 times 10 to the 5th seconds to start at 0 at the original concentration and decrease through 2 half-lives so that we have 25% remaining. And we can repeat this logic. Here is a point at which we have half of the 25%, or 12.5% remaining, which is equal to this point 3 half-lives. So we could come through here, cross another line out to here and here, and be accurate. Time to get to right here and here would be 3 half-lives, or 3 times 3.47 times 10 to the 5th seconds. 1.04 times 10 to the 6th seconds. Like that. So 12.5% remaining. Well, we can continue with this logic, splitting each one of these distances in half again and again, where the value for this one would be 0.0625% remaining, and the value for this one would be 0.03. I think they're talking 0.03125, a fraction left, or 3.12, 12.5%. Okay. Actually, I should be saying 6.25 and then 3.125. I'm just dividing each one in half. I'm sorry, I'm just thinking fractions. Okay, remaining. So this one would be, this one was 3 half-lives. This would be 4 half-lives. And this one would be 5 half-lives. So that's 4 times 3.47 times 10 to the 5th seconds, which is 1.39 times 10 to the 6th. 39 times 10 to the 6 seconds, 1.39. And this one is 5 times 3.47 times 10 to the 5th seconds, which is equal to 1.735 times 10 to the 6 seconds. Now, keep in mind that how it depends on how the question is worded, that how you approach the solution to it. If it just simply asks for half-life, first half-life is calculated using the expression here. That's first half-life. And you solve for t to the 1/2 and substitute the k value, and you can get the first half-life. But if the question asks you how long does it take to get to 25% remaining, first half-life is 50% remaining. 50% consumed, 50% remaining. The second half-life is 75% consumed, but 25% remaining, and then so forth, and then 12.5% remaining, 6.25% remaining, and 3.125 remaining. So the half-life equation and the decay equation deal with what is the remaining amount when you make those calculations.